In talking about chiral molecules so far, we used to represent them with their full perspective drawings. An example could be shown here with the structure of amino acid alanine, which is shown here in its perspective projection. And this projection is completely comprehensive. It shows us everything, and it's very instructive for teaching stereochemistry. However, once you already absorb these principles of three-dimensional relationships in organic molecules, you start having a need to process these structures a little faster than drawing out the perspective drawings. And also perspective drawings tend to get a little crowded in structures which have more than one chiral stereo. And so stereochemists have been seeking for ways to simplify the projections of chiral molecules without losing any of the information. And the topic that we'll talk about now is one of those simplifications, which is very popular, called the Fischer Projections. And it should come as no surprise that these Fischer Projections have been developed by Emil Fischer, who was a carbohydrate chemist. And carbohydrates, which are basically sugars, have up to 7 stereocenters. So clearly he needed to simplify these projections so he could work with them relatively quickly. For his work on carbohydrates, Emil Fischer got a Nobel Prize in 1902, and it's still regarded as one of the greatest pieces of chemical logic. But to analyze simple Fischer projections, we'll start with the structure of alanine, and we'll go through a couple of simple steps to get it to the Fischer structure. So the first thing that we will do is rotate everything a little bit around, in plane around in this direction, to get a structure which looks like this. And what this rotation did is it created two planes. One plane is in the plane of the screen. It contains COH group, C, and CH3 group. Well, the other plane is exactly perpendicular to the plane of the screen and contains nitrogen, carbon, and hydrogen. Okay? Now, if we recall our presentation of Newman projections and look down this way, what we will see is our nitrogen on the left pointing towards us, carbon in the middle, and hydrogen on the right, but still pointing towards us. Pointing away from us will be the COH group on the top and the CH3 group on the bottom. Okay? And it's important to understand that this structure still represents exactly the same molecule as the original structure, with all the complexity that is inherent to that molecule. Now, the simplification which is inherent to the Fischer projections is that it takes these structures with wedges pointing in the horizontal direction and dashes pointing in the vertical direction, and then replaces all the wedges and dashes with a simple cross. Okay? And now this thing is simple, but we always have to bear in mind that the horizontal lines point towards us, so above the plane, whereas vertical lines point away from us. And also the central carbon is often omitted. And if we keep these three rules in mind, the Fischer projections basically do not lose any information. The problems come when we forget that the horizontal lines have to point towards us and the vertical lines point backwards, because then at that point we start switching the two enantiomers, which is something we do not want to do. And so once again, it's important that we have vertical lines be dashes and horizontal lines be wedges. So here is exactly the same structure again. Now this convention sort of has a couple of general points that come with it. The first one is that you can rotate these structures by 180 degrees. Because if you start with a structure which points this way, and then rotate by 180 degrees in either of the two directions, what you will get to is the following. Your hydrogen will be here, NH2 will be here, CH2 will be here, and COH will be here. But the point is that still the horizontal lines are wedges, because if you rotate by 180 degrees, you did not switch the horizontal and the vertical lines, you just switch the two sides of the horizontal and vertical lines. And so this structure is still accurately representing the original molecule of aniline we started with. Since the 180 degree rotation does not switch the horizontal and vertical. That immediately leads us to the second point, that 90 degree rotation does switch the horizontal and the vertical lines, and basically in doing so it switches you from one enantiomer to the other, and so that is something you do not want to do, and so you should never rotate by 90 degrees, because that will confuse you since it will give the opposite enantiomer. Okay, so these structures you can rotate by 180 degrees, but you should never rotate them by 90 degrees, and also you should also never flip them. Okay. Other manipulations of these structures are still relatively straightforward. So if you want to construct a mirror image, you just do that. It's exactly the same as we have perspective structure. So if this is our original molecule of alanine, we can construct its mirror image, and we will see later that these two will be enantiomers. If you want to go out and look for symmetry, you can do that in Fischer projections as well. If you see a symmetric Fischer projection, that means that the molecule is symmetric. So here is a Fischer structure of an achiral molecule, and we can quickly realize that there is a plane of symmetry sigma here. So this is really achiral. We can also look at molecules that does have chiral centers, but in such a relationship that there is a plane of symmetry in the molecule overall still. So here it is. Here. And both of these molecules are achiral, and we can clearly see that from our Fischer structures. Okay. Finally, if we are to look for RS nomenclature, we can do that as well in our Fischer structures. So again, if we have a molecule, and now this is not going to be a little different, which looks like this. The thing that we must remember about our RS nomenclature is that our lowest priority substituent has to point backwards. Okay? And in this case, this is substituent number 1, this will be 2, this will be 3, and this will be 4. And hydrogen is on the top, which means that the vertical lines are dashes, so they point backwards. So we already have our substituent 4 pointing backwards, and so we can just simply look at 1, 2, and 3, and in doing so we see that this is an R enantiomer of alanine. But what if we had our structure drawn the way we drew it already? This way. And so now our priorities would still be the same. This would be 1, 2, 3, and 4. But our hydrogen now will be pointing upwards. In those cases, what you might want to consider is using a trick, right? Because we know our hydrogen is pointing upwards, we still can look at our sequence of 1, 2, 3, and then simply invert it. Because since our hydrogen is pointing upwards, our configuration is going to be wrong. We need hydrogen to point backwards. But since we know it's going to be wrong, we can get that wrong configuration and then switch it to the correct one, since we have only two choices, RS. And in this case, this structure would looks like R, but hydrogen is in the front, which means that we need to invert it, and means that the true structure is S. Okay? I don't know how helpful this trick is, but what I noticed is that a lot of people have trouble with rotating these structures in three-dimensional space. And this procedure allows you to avoid rotation. You basically assign a configuration without changing the molecule at all, and then convert that configuration into the correct one. So it's up to you whether you want to use this or whether you really want to rotate your molecule fully. Again, these things are very good to practice with models, especially conversion of perspective structures into Fischer structures. This will conclude our today's lecture, and the next time we will start talking more about molecules which have multiple stereocenters and certain facets of their stereochemistry which are unique to them and make them quite distinct from molecules with just single stereocenter.